Okay. All righty. As people are still coming in, I'll go ahead and do some announcements so that we can start on time. Today, I am going to introduce our speaker. We do have a hard stop at 4:59 because we do have another webinar right after this one. So my name is Jasmine and I am the AAS meetings coordinator. We will have time for question answers about the 15-minute mark. You'll be able to ask your questions in the chat box or unmute yourself. I do have my Slack channel open, so if you ask questions in there, I can read them out loud as well. And with that, I'll introduce our speakers for this evening. It looks like we have 3 speakers from Caltech. So we have Perry Teplitz, Phil Appleton, and James Colbert.
Thanks. So I'm going to give a presentation that will give an overview of Euclid and the opportunities for archival science by the US community using Euclid data, and then Phil and James will help me answer questions. And I should say that I'm giving this talk on behalf of the Euclid team at Caltech IPAC, and also on behalf of information by the Euclid Consortium. So Euclid is an ESA M-class mission to study the geometry and nature of the dark universe. Euclid is expected to launch in 2022, so next year. The expedition is a 6+ year lifetime. It will operate a 1.2 meter telescope at L2. The Euclid Consortium is an international organization with more than 1,000 scientists and engineers who have developed the instruments and are managing the surveys and will conduct science using the proprietary data. NASA is participating in Euclid in 3 ways. NASA contributed 16 state-of-the-art infrared detectors and associated cold electronics, which have been integrated into near-infrared instrument on Euclid. NASA also selected 3 science teams to join the Euclid Consortium and participate in the proprietary science. Those began with 40 scientists at the time of selection, and now there are about 100 people in the US, scientists and engineers, who are participating in the consortium. And finally, NASA has established the Euclid NASA Science Center at IPAC to support US-based investigations with Euclid data, both by the selected science teams and more broadly by anyone in the US who wants to do archival research with public Euclid data. I'm the task lead for NSci, and so I'm happy to answer any questions here or in the future regarding Euclid. Euclid is a cosmology experiment designed to study the nature of dark matter and dark energy. This is the famous pie chart showing the distribution of matter and energy, which, as you know, is determined by Planck, and as you know, it is dominated by dark energy. Euclid is optimized for two of the primary probes of dark energy, although other probes will also be conducted. The first of these probes makes use of gravitational lensing. As you know, the path of light from a distant object can be deviated by the presence of foreground mass concentration, and this image here shows the example of a strong lensing effect where a cluster of galaxies, which you can see in the middle, changes the observed shape of a galaxy that is seen behind the cluster and can lead to very dramatic images where those galaxies which have regular shapes become streaks or arcs in the image, which you can see on the right-hand side. Euclid will be able to study strong lensing, but the primary probe that it will use in the cosmology experiment is the weak gravitational lensing effect, which is similar, whereby foreground concentrations of dark matter can subtly change the shapes of background galaxies. And this is an effect that is largely measured statistically. In this simple model here on the left, you can see very regular shapes to represent galaxies, and on the right, you can see the effect of a foreground dark matter concentration that would subtly change the shape of each one, but together there's a systematic effect in the way the shapes are changed, allowing the inference of how that foreground dark matter is concentrated. This image shows an example of doing that. One of the first examples using Hubble in the cosmos field, where shapes were measured using optical images from Hubble, and then the dark matter concentrations shown at the bottom were inferred from that. Euclid will do this on a very large scale in the extragalactic sky to study the evolution of the clustering of dark matter as a function of time in order to understand the effects of dark energy on that growth of structure. The other primary probe that Euclid will employ goes by the somewhat difficult name of baryonic acoustic oscillations, or the simple acronym BAO. In this method, the characteristic clustering scale of galaxies observed in emission at various redshifts is compared to the primordial density scale as observed by Planck, to again trace the growth of structure. You can see on the right the power spectrum of clustering with a characteristic peak at that scale that will be compared with the primordial one. The original density peaks were set when the universe was a plasma, and so information traveled by sound waves, hence the name acoustic in the method. Euclid will obtain spectra to get redshifts of galaxies for this method. All right, so that's the goal, is to do those two primary probes, and Euclid has been optimized to do those particular experiments, although it will be useful for many other things that I'll talk about in a minute. This slide is just a quick overview of Euclid as a whole. There are two instruments on Euclid. One is the near-infrared spectrometer and photometer that goes by the acronym NISP. It has a field of view of about a half a square degree, and it consists of the 16 near-infrared detectors contributed by NASA. The visible light imager, or VIS, has about the same field of view with 36 CCDs and a high spatial resolution. Euclid will also use significant ground-based optical photometry in order to measure the photometric redshifts that are needed in order to understand the weak lensing effect. The data release policy on the ground-based data is still TBD. Let me show you a few pretty pictures of the instruments. This is the focal plane where you can see VIS and NISP in their arrangement with the M3 mirror. There's a dichroic to split the light by wavelength. This is a summary of the VIS instrument. VIS will have 36 CCDs with a field of view of half a square degree. You can see that here compared to the size of the moon. In the middle, you can see a simulated image of the many galaxies that VIS will be able to detect at one shot. VIS will do this with a wideband filter covering 550 to 900 nanometers to maximize the signal for the shape measurement. So it doesn't allow photometry that would be necessary for measuring photons. It's entirely dedicated to measuring the shape, and it will do this for 1.5 billion galaxies, reaching quite deep, 24.5 magnitude at 10 sigma. And it will do it with high spatial resolution with a plate scale of 0.1 arc second. The photometry for the photoz's for the weak lensing method will come from a combination of ground-based data together with the data from NISP. NISP is an imager and spectrometer. It will obtain photometry in the Y, J, and H filters to support that photometric redshift measurement, and for all of 1.5 billion galaxies. And it will obtain spectra to get redshifts of about 30 million galaxies by detecting the H alpha line, which at redshifts of around 1 to 2 shifts into the near infrared. In Euclid's main survey, this will be done with a red grism covering 1.25 to 1.85 microns, although the instrument does have a bluer grism that will be used in selected deep fields that I'll talk about in a minute. It has moderate or low moderate resolution for spectroscopy, or about 380 for a half arc second source, and it has high spatial resolution of 0.3 arc seconds per pixel, but not as high as the VIS instrument. In the background here, you can see simulations of the spectroscopy that will be obtained, which will be obtained with the slitless grism mode, where the light from all the sources in the field is dispersed at once without an entrance slit. And in the upper left-hand corner, you can see photograph of one of the detectors in the lab. Euclid's main survey will be a wide survey covering essentially the entire extragalactic sky. 15,000 square degrees are planned, excluding only a couple of small regions of bright foreground contamination. Euclid will also obtain data in 3 deep fields that combined will have 40 square degrees. These are at the north and south ecliptic poles and in an extended region around the CDF south. In addition, Euclid will have some calibration fields totaling about 4 square degrees for self-calibration and other necessary monitoring. In the upper left here, you can see the buildup of the Euclid surveys where the color indicates which year it's planned for. You can see we'll eventually cover the whole extragalactic sky. Euclid will use a step and stair coverage method to fill in gaps between the detectors, although the wide survey is essentially 4 exposures per filter per pointing. I think hopefully I did not skip a, yeah, okay. So that's the basic survey that Euclid will do. Again, focused originally on these 2 primary probes of cosmology, but because we're obtaining high resolution imaging and photometry and low resolution spectroscopy over the extragalactic sky, these data will be used for a wide range of other extragalactic and galactic astrophysics that will be a huge resource for both the consortium and for the broader worldwide community to conduct archival research. I won't read through every word here in the interest of time, but these data will be applicable to everything from the structure and history of the Milky Way halo to galaxy evolution, both at cosmic noon and at high redshift, to studying galaxy clusters and to studying quasars. The Euclid data will also be very valuable in combination with other surveys. In the coming decade, there's a lot of, there are several very large surveys planned, and so Euclid's photometry will facilitate doing research in lower resolution, spatial resolution surveys where Euclid can point to the distribution of light. It will also improve our understanding of dark energy when used in combination with other studies. All right, as I said, Euclid data is planned to go public to the entire world. The plan is to release the data within about 2 years of acquisition. On the right here, you can see the plan for the public data releases. These dates here are referenced to the start of nominal operations rather than to launch. The current plan is for a 1-month transfer phase and a 2-month performance verification phase. So unless there are unforeseen problems, you can just add 3 months to the numbers here. The plan is first to do a quick release of a small area of data, 50 square degrees, which is not small on the scale of current surveys, but is small compared to Euclid's goal. And that quick release will give the community some data to immediately do some research with and to prepare for research with the much larger data that will be available soon thereafter. That will be 14 months after the start of nominal operations. A year later, there'll be data release 1, which is the first of 3 major data releases. DR1 will include 2,500 square degrees. And after that, there will be interleaved, quick, and large data releases. The large data releases occurring 2 years after DR1 and then 3 years after that to eventually release the entire survey. The Euclid data will be served by the ESA archive system at the Euclid archive system at the ESA archive at ESAC in Madrid. And the same data or subset will also be available through the NASA IPAC Infrared Science Archive, or URSA, at Caltech. You can see us at the IPAC archive booth if you have other interests in URSA. Euclid will be big data. It's a petabyte scale data project, just based on the data products from the spacecraft, and then significant enhanced products that will be derived from those. And then there will be significant ground-based data released as well, although the release policy on that is TBD. The Euclid science with this petabyte scale data will be applicable to many different investigations. It will be a huge resource, and we expect that it will be used by many people. NASA anticipates supporting this research through the Astrophysics Data Analysis Program, ADAP, in the same way that NASA supports research from any other mission to which NASA contributes. We expect there will be essentially a flood of proposals once these data are released. We know from Spitzer and Wise that each of them were used in about 40% of ADAP proposals in their first year. If you want some more information on things NASA might consider that we've advocated for in terms of how ADAP can support Euclid research, you can see the white paper that we submitted to the APC call for Astro 2020. I'll just put up as my last slide here that again, we're the Euclid NASA Science Center at IPAC, NSci. If you want some more information about Euclid, you can see our website, or if you have any questions beyond those that you would like to ask here in this webinar, you can see us either at the IPAC booth here at AAS or at the help desk link also here on the slide. And with that, I'd be happy to answer any questions.
Alrighty, thank you. If anyone wants to unmute themselves or put them in the chat box, I can read them out loud.
I realize that we're midway through a week of many, many Zoom meetings, and it may be difficult to engage too much more in this forum. So I thank you for participating in the virtual version of this.
Yes, thank you all.
Well, let me ask my colleagues, Phil and James, if there's anything I forgot to say that I should have included.
No, I think you covered it pretty well, Harry. I can't think of anything.
All right.
Yeah, I mean, I think I would just emphasize that, you know, we're talking about 2,500 square degrees up to eventually 15,000 square degrees of, you know, space stable near infrared data and with redshift. I mean, it's going to be quite a database, I think, for people to use as a tool. I mean, you said that clearly, but I was doubling down on that. I think it's going to be quite a resource once it's available.
Right. And I would encourage people to come to our website for the latest news as soon as there are any announcements about either the future, either related to launch or data releases or future conferences that will be including Euclid. We try to cover those on the website. So we hope to be a resource for that. All right.
Harry,
Well, I know that
there's one. I was wondering if you wanted to say something about the non-Euclid sort of ground-based data and how that would be served in terms of the different surveys and how they contribute.
Sure. So Euclid is going to use data from a variety of ground-based facilities. The policy for releasing the data is still being negotiated with the individual projects, but and it has to be negotiated. It's not going to be a uniform solution, but because Euclid is the whole extragalactic sky, it will include areas that have already been surveyed by the Dark Energy Survey, DES, which is one of the primary sources of ground-based photometry. The Rubin survey will also be in similar areas, and there are negotiations with them to share products, although of course any release of Rubin data would probably be through Rubin. Euclid has negotiated some dedicated observations to be taken both by the Canada France Hawaii telescope, through which Canada has joined the consortium, and on Subaru, through which Japan has joined the consortium, to make sure that all of the fields are covered. Once the negotiations are settled with each individual projects, I believe that the plan would be to have relevant data from which Euclid, hopefully relevant data from which Euclid photometry was extracted could be released. And in cases where that can't be negotiated, at the very least to release catalogs where the photometry itself that went into the PhotoZ is included in the Euclid catalogs.
So would that include the Q1 release, the 50?
It is the Q1 data set is not fully defined. It's being negotiated at the moment.
Yeah,
I would not be surprised if Euclid chose to restrict Q1 to Euclid data only in order to have some more time for the negotiations. But it's not determined yet. And Q1 being only 50 square degrees, of course, it could be a special case. But the answer is we don't know yet.
yeah. I mean, obviously, Euclid data is more useful when it's combined with these other surveys for certain
Right.
kinds of things. Yeah.
And in areas like the Euclid deep fields, there's a lot of other data already in the archives for that. For example, the Spitzer Space Telescope spent almost a year and a half covering data that happened, both dedicated surveys and just happens to be in the right place for the Euclid deep fields. Okay. If no questions have appeared in the chat, I couldn't figure it.
No, there's no questions in the chat.
All right, then Phil, maybe we can just finish a few minutes early, you think?
Yes, if there's no more questions, we can end the
right.
session early.
Let me just check with Phil and James if they have anything else they want to say.
Yep, no, that sounds okay with me.
Yeah, I'm fine.
All right.
All right.
Thanks.
Thank you so much, Harry.
Everyone for joining us, and definitely come see us at the website or at the IPAC booth if you think of a question during the week.
Okay, thanks, Eric.
You have a great evening, everyone.
All right.